All right. So we start off math connections. Let's see here. What do we have? 1 through 3, 5, 11, 18, 20 to 22. So 20, 20, 22. So 3, 6, 7, 8, 9. So 9 questions. And these do kind of focus on pieces that we've seen in some of the other videos. Can you construct a triangle using the links 4, 5, and 7? Why or why not? Now, if you want, you can always start building some of these shapes with your compass and straight edge if you wanted to. Remember, you do have a ruler, they exist. So you can measure out, here's a 4 centimeter length, here's a 5 centimeter length, here's 12 centimeters. If I was to give you a tip, my recommendation is to draw the longest length first and then use the other ones to kind of see where things could intersect. If you want, I'll try to remind myself to show with the compass here in this video to kind of show kind of how to construct those. Okay. Let's see here. A triangle has two sides of length 10 and 14. What can you say about the length of the third side? Okay, this ties together with number 1, and it ties together with a property we're going to find and discover in class. So I don't know if I want to give too much away right now, but there is a relationship between the third side and the other two sides. So any two sides of a triangle, we can do something with those to create a relationship with the third side, if it is indeed a triangle. Let's see for the next one in the figure below. Answer the following. Point C is the intersection of AE and BD. All right. Now notice this is where I think sometimes students do get a little bit of trouble, but it tells you an if statement. So if angle 1 is equal to angle 2, right? If those are, then tell us two congruent segments. If you have congruent angles, what does that tell you about segments? And that is a nice little property about isosceles triangles. Then we come down here. If ACB and DCE are both isosceles, so when you look up there, my recommendation is when you see ABC and DCE are both isosceles, mark them ACB. Okay, so if ACB is isosceles, because clearly there's one long side, and DCE. Okay, DCE. Maybe I'll mark those with 2. If those are isosceles, does that mean the triangles are congruent? And yes, we do get an angle here in the middle, which we know the angle has to be the same because of something from chapter 11. So again, that's what it's asking you to do. Take the if statement, mark it on there if you need to, and then answer the question. Okay. All right, let's see here. What else? That was 1 through 3, 5, and 11. So we've got a kite, and the congruent segments are listed with tick marks. They want you to argue that the diagonal bisects angle A and angle C. Now, if you're looking at that picture, you may think maybe it does, maybe it doesn't. But you're trying to prove that the angle right here has to be the same as the angle below it. All right? And it also says the same for C, so that this angle would have to be the same as this angle. Are those two the same angle? And if so, why? Okay. May be true, may not be true, but that's what we're looking to do. Nudges in the right direction. Look for congruent triangles. Okay. Look for congruent triangles. We know congruent from this chapter. We need side, angle, side, or side, side, side. We know these pieces. So if you don't have those, look to find them. Try to find which pieces would line up. Okay, so I said 5, then I said, let's go over here. 14, okay. So here are two shapes on dot paper. Answer the following. Why are AB and CD congruent? Okay. Now, if you look at this, you might be able to tell that they, you could mention this based on either a relationship between triangles, if you want to verify that, or you could make an argument based on creating the same length. So I would take either one. I would take either one, especially on dot paper. Okay, and then why are these perpendicular to each other? Why is AB perpendicular to CD? Okay, so your goal is to prove that those are perpendicular to each other. And I think you'll be able to do it. I think you'll be able to do it. That's what I believe. But again, if you want to show that they are perpendicular to each other, think about what you're trying to say. This would be my tip. Think about the question that's being asked. The question being asked says, prove that they are perpendicular to each other. So you need to prove these are 90 degrees. Before you know they're 90 degrees, you really just need to prove that they're the same, because if they are the same and they're supplementary, they have to be 90 degrees. So look at those two angles and try to find, is there a triangle I could use that would show me that those two angles are the same? Look for that. Find yourself a congruent triangle. Okay, so that gives me 1, 2, 5, 5, 11. Oh, shoot. I did 14 because I looked up there. Dang it. Oh, shoot. Well, I just gave away what used to be a test question. Never mind. Ignore that one. Pretend nothing happened. Okay, let's go. 11 is what I needed, and 11 is Thales theorem. This is kind of a cool theorem related to the shapes that you see here, and your goal is to prove Thales theorem by using the following suggestions. If you look, what they're trying to say is they're giving you some pretty big tips, and the tips include the fact that you have in a circle the same radius. So when you create a triangle like the one right here, if these sides are the same, then the angles next to them have to be the same. So you'll notice that they are listed as X and X, right? And then likewise, create another triangle right over here. And the fact that this has the same radius, so therefore potentially a different angle there. So your goal as you do this is you want to prove, use the fact that we know something about the sum of the triangle measures. And don't forget, there's a third triangle that's being made here. It's this bigger triangle. So that's what I would recommend. Think about bigger triangle, think about smaller triangles, and see what you can get from there to prove that this angle at B is 90 degrees. That's your goal. All right. There you go, Thales theorem. And 18, and then 20 to 22. So question 18. Oh, now we're getting to the questions from the classroom. So here we go. Teacher challenges students to prove using side, side, side. So the teacher sketches a triangle. And notice when they say things like AC is equal to BD, right? You want to mark that on your shape. If the teacher sketches it and it says AC is equal to BC, then mark that on the shape so that you know those are exactly the same. And provides the first step in the proof by connecting C with the midpoint of AB. So again, when they tell you something is the midpoint, mark it. It's the midpoint. They're telling you this. Now, in other proofs, if you don't know it's the midpoint, you can't make that. But because they told you it's the midpoint, you absolutely can. And your goal is to try to prove theorem 12.4, which is to say that CD is either perpendicular bisector or an angle bisector of an isosceles triangle. So look at the theorem, see which one you're trying to prove, create similar congruent triangles. And she said she's challenged them to use side, side, side. So that's what you want to use for this one. There's number 18. And I think we have 20 through 22 were the last ones. Let's take a look over here. 20. All right, Joel, what do you got? Joel claims the following triangles are congruent by side, angle, side. All right. And he lists them. So you can see we got side, we have an angle, and then we have a side. Is that what is required for side, angle, side? This is the question for you. How do you respond to what Joel is presenting? On a test, go to 21. On a test, a student wrote the answer A, B, O. We've talked about this a little bit in chapter 11, and I tried to say very clearly why you want to be very careful with this notation. Think about when to use this symbol and when to use this symbol. Which one would you use where? Okay, that's my tip on 21 if you needed it. And 22, Zara claims that in spite of the fact that every triangle is congruent to itself, which it is, she claims that ABC is congruent to BAC is generally false. Now, that would be interesting. However, if AC is equal to BC, then the statement is true. Now, again, whenever you see proofs that involve things with triangles, my recommendation is draw the triangle. So if you were doing this one, I would say here's ABC, right? Okay, there's my 3 points. Now, if you were trying to say, is this congruent to BAC, the points are really right up here above you, right? But notice she's going to put a condition on it. She's going to say if AC is congruent to BC. Okay, so if this is an if statement. So if that is true, if AC is congruent to BC, now can she make this claim over here? Still have to have a reason for it, but I want you to check through her reasoning. She may be correct. She may be off. She might be very close, but I want you to think about how you can make this statement. And the reason is you will oftentimes see students or others kind of writing things down in a way that you know a triangle is congruent to itself. So if they say ABC is congruent to triangle ABC, remember, that means angle A has to match with angle A, B has to match with B, and C has to match with C, which they definitely do by the reflexive property. But if you write it in a different way and you say triangle ABC has to be congruent to triangle BAC, then those are slightly different, right? Because now we're saying angle A has to match here, angle B, and then angle C has to match itself, which is fine. But we're also saying some components about segments. So BA to AB, and then some additional components. So think about how those parts have to match up, the corresponding pieces, and I think that'll get you on the right track. Ooh, I said I was going to try and do a drawing for you. Okay, let me go back. See, almost lost it. Getting old, that's all it is, I'm sure. I said, can I construct a triangle? Okay, so I want to show how we can construct a particular triangle using our compass and straight edge. Let's see, let me get a blank sheet of paper. I'm going to switch over to my amazing document camera. It's such a cheap document camera. You can kind of see it sitting right here. This is it. It's not fancy. Don't yeah. But it seems to be doing the trick, but please tell me if you have issues with it. Here we go. Are we here? Okay, here we go. All right, all right, all right. So I'm gonna pop this sucker open. Oops, see, I tipped something. It's a piece of garbage. Okay. All right. Is that, see, now it's all twisted. Why is it doing that? Go up and down. There we go. All right, that's fine. That's fine. Okay, here comes my compass. Here comes my straight edge. I've got my pencil. So what I'm going to do is I'm going to create some side lengths right up here. Okay. And I'm going to say, I want you to build me a triangle that has those side lengths. All right. So let's see here. I would probably start with just a line as well, somewhere down here. Doesn't matter where. Okay, nice and long. All right. Well, shoot, that is kind of curved, but that's fine. So take your compass, and I'm going to use, because mine has a pull apart. Some of you might have the little levers on here. Press the levers in before you decide to pull apart, because the levers actually help lock things into place a little bit better. Okay. So I want to keep this exact length. So pokey part goes in, adjust this a little bit. There we go. I've got that length. Now come down here and make sure you make a point. Make a point as your kind of starting space, so you know exactly where to put your compass, and then turn that across. Okay. I've just made that length right here. Maybe it's 5 to 10 centimeters, whatever it is. I can measure that out up here if I wanted to. And now I've got this piece locked in place. Okay. Next, come back and do the same thing for the next one. Okay. So I bring this in. Okay. About right there. That looks pretty good. That looks right on. Okay. Take the point, put it down, and then watch this. All I'm going to do is I'm just going to turn an arc. Okay. I hope that's long enough. I'm not sure. Maybe I'll go a little further just in case. I'm not 100% sure because this last side looks pretty small. Okay, so let's do the same thing here. We put our point here and adjust. Bring it on in. Okay. Make a little turn, make sure. Okay, we're good. Take that length to the third side, put it right in here, and then turn. Oh, I did need to extend it. There we go. So take a look at what we've built then. The shortest side is right here. The medium side is right here. And let me put those together with my straight edge. Okay. And there we go. So I have now built a triangle where the three lengths up here turn out to be the three sides. And so we can see this one is definitely constructible. And you can even label this, right? You can see the three sides are all different. So this is definitely scalene. Not only is it scalene, I can look at that angle and say that is a massive angle. So this is obtuse, is definitely bigger than 90 degrees. So obtuse scalene triangle is what I just built right there. All right, hope that helps. If you have other questions, let me know. Okay, let's get back up here. All right, off you go.